participants. Welcome to today's FGP session on 5G. Today is 10th April. We have back-to-back two sessions today. One session will be taken by Dr. Himanshu Bhusan Mishra of IIT-ISM Dhanbad. And second session will be taken by Sri Ashok Kumar Sir, DDG, DOT. The first session, topic of the first session is orthogonal time frequency space OTS waveform for next generation wireless systems. Dr. Himanshu Bhusan Mishra will be taking this session. Dr. Himanshu Bhusan Mishra is an accomplished scholar with a rich academic background and extensive contribution to the field of wireless communication technologies. He completed his BTech degree in Electronics and Communication Engineering from DPUT, Odisha in 2009, followed by an MTech degree in Communication and Signal Processing from esteemed ECE Department of NIT Rourkela in 2012, and PhD in Communication and Signal Processing from distinguished Electronics Engineering Department of IIT Kanpur in 2016. Currently, Dr. Mishra serves as Assistant Professor at the Electronics Engineering Department of IIT-ISM Dhanbad, where he actively engaged in research and teaching. His research interests lie in the forefront of wireless communication technologies, particularly focusing on parameter estimation, detection, and optimization for the next generation of wireless communication systems such as orthogonal time frequency space OTFS, intelligent reflecting surface enhanced OFDM, IRS, OTFS, ISAC, among others. Dr. Mishra is dedicated to realizing the potential of his research by working on real-time implementation of proposed algorithm on software-defined radio network. His academic achievements include receiving the Best MTech Award in the Communication and Signal Processing domain from IIT Rourkela in 2012. Dr. Mishra is currently at the helm of 4 DST-funded projects and 1 TIS-funded project in the domain of beyond 5G wireless communication, showcasing his leadership and expertise in the field. Dr. Mishra's contribution to academia are further underscored by his prolific publication record, with over 20 research articles published in reputable journals and conferences. Notably, 2 of his research articles on OTFS have been recognized as best reading article in the IEEE Communication Society, attesting to the significance of his work in advancing the field of wireless communications. With this short bio, I invited Dr. Himanshu Bhusan to take over this new topic, very pertinent topic. So, Dr. Mishra, over to you.
Okay. Thank you very much for this introduction and giving me such a good platform. I am thanking to DOT. So, okay, so my screen is visible, I think.
Yes, sir. Yes, sir. Very much.
Okay,
yes, visible.
Yeah. Okay, so I would like to present here as the topic already told by Madhukarji. So it is OTFS, orthogonal time frequency space waveform for next generation wireless system. So here I will introduce first why we are going towards OTFS. Next, I will give the complete frame structure of OTFS waveform scheme. And after that, I will highlight some key research of our group and also tell you a lot of research on what future research also we can do on this. And some key references I will tell you later. So first of all, coming to the point, first point is the representation of wireless channel. How we can represent the wireless channel. So we can represent wireless channel impulse response in 5 different manner, or you can tell 5 different domains. One is time. This is known as time and delay. T represents the time and delay. Impulse response, time and delay. This is the frequency response. You can tell time frequency. This is the delay Doppler. Another one is Doppler and frequency. So mostly we are focusing these above 3, that is time delay and time frequency. All of you know that delay time and time frequency. We are dealing with OFDM. So here we are converting the time domain impulse response through Fourier transform to the time frequency. So here in OTFS, one catch we have to use, and we have to exploit the delay Doppler structure of the channel. We'll see some nice advantages of delay Doppler structure of the channel. So let me come to the point. So here some this I will discuss as FFT. What is that later on? But just for your knowledge, I'm telling. This is a two-dimensional transformation. If you want to transform from time frequency to delay Doppler, that you can do through the SFFT, and reverse delay Doppler to time frequency, do inverse symplectic finite Fourier transform. So basic, we know that CP OFDM, that is a key OFDM, that is a key physical layer technology that we have we are using in 5G also. So here that all of us know that there is this type of transmission. We have transmitter side, we have IFFT, receiver side, we have FFT, and due to this reason, if wireless channel is frequency selective slow fading, then we are getting advantages of using the CPU OFDM. That means we can directly use the one tab equalizer. Okay, one tab equalizer for any OFDM technology, that we can to decode the transmitted signal in the frequency domain. So that means you can tell that we are completely mitigating the effect of inter-symbol interference that will occur during the frequency selective channel. So that we can mitigate using OFDM technology. But if the channel is time varying, if the channel is, I told this point, so if the, and another point, as you all of us know, that the when can you mitigate the inter-symbol interference? If you use the length of cyclic prefix should be equal to L minus 1, minimum length has to be equal to L minus 1. What is L? L is the channel order, that means the length of frequency selective channel, or you can tell if the channel is L tab. So another point is, that is the key point, that if the channel is frequency selective but highly time varying, that is the scenario we can see in the vehicular, when there is aircraft communication, in any vehicular communication, all these things. So here you can see that there is, due to highly time varying channel, Doppler shift will come into the picture. So due to the Doppler shift, what will happen? The OFDM, the orthogonal properties of the subcarrier frequency, that will no longer exist. So that will create an interference that is known as inter-carrier interference. Okay, so in order to mitigate this, OTFS came into the picture. So that is the motivation why people have developed the OTFS technique. So one key point of OTFS waveform is that it exploits one important nature of the time delay Doppler channel, which is a time invariant nature. We can tell the delay Doppler domain. If you see the channel in delay Doppler domain, it will be approximately time invariant nature. I will tell you why it is approximate time invariant nature. Then second point, you can see that they have already you can check some good papers I have given you the starting. If you want to see the Professor Chokalingam's paper from ISC, you can see that they have already done the simulation that you're getting better beat error rate in comparison to the OFDM technology if they are going with a high speed, that you can check the 30 km to 500 km per hour in 4 GHz band. And another, these are the points that advantage will get using OTFS. Now, how I can do implementation of the OTFS, that I will tell you in the later. So let us, first point, as I told you, that OTFS, the key point is that it's exploiting the time invariant nature of the delay Doppler channel. So let us see how the delay Doppler channel response will be looking like. This is the delay Doppler channel response. At tau I is the delay shift, this tau represents the delay, and the nu is the representing the Doppler. So at particular delay and Doppler, you have the channel taps. This you can, P can known as the number of paths, or you can tell at least the number of dominant path that has been occurring due to the number of clusters present in the environment, and each path is associated with a delay tau I and a Doppler nu I. Then you can represent, this is a standard model of you can tell channel impulse response in delay Doppler domain. Here, the tau I is the ith delay. That means the channel means delay associated with the ith path can be represented if you consider 1 by m delta f. That is nothing but delay resolution factor. Okay, 1 by m delta f, the delay resolution. So it can be that means represented by one integer li, so that you can tell that li is the integer tab corresponding to the delay tau I. Similarly, considering the Doppler resolution as 1 by nt, ki will be the integer Doppler tab corresponding to the Doppler nu I, and alpha you can take some fractional Doppler. Here also there may be fractional delay, but what you can tell you that in practice m is too much high. M is same as your number of subcarriers. Okay, in practice number of subcarriers you can see that 1024 like this. So if it is too much high, so there's very less, the resolution factor will be reduced. So you can have you can easily approximate to the nearest integer. The tau, that means tau I, can be approximated by be taken by the, if you sample it, so you can have nearly integer, that is li. But in practice, since n represents the latency, the if n is more, so latency will be more. So we generally will do n is less. So that's why what will happen in Doppler, some fractional part will come in this. But in this analysis, I will tell you by assuming integer delay and integer Doppler. All this mathematical analysis I will do. So here the point, let us come to the pictorial this view that you can see here. So there is a transmitter. This one is the receiver. There is various paths. So left hand side you can see the channel has been represented in the delay Doppler domain. Right hand side in the time frequency domain. If you can see here how many paths, each path is associated with some delay and Doppler. You can see the left hand side, that this side, that here few number of channel tabs are there in the delay Doppler. However, if you can look into the time frequency domain, it is a every almost all time and frequency you have channel tabs. So whenever we will do in practice the channel estimation problem with solving the estimating the channel, the delay Doppler if we do, that will be very few number of channels are required to be estimated in comparison to the time frequency. That is one advantages of channel representation of the channel in the delay Doppler domain. So this is somewhat little bit time by little bit delta time later it has been taken, this picture. So this I have taken from this paper, you can see. So here I will tell you next, that is a very good example of why the delay Doppler domain, if you take the channel, why it is approximately time invariant. You can check here that it has been real-time experiment has been done by Professor Viterbo research group of Monash University. What they have done is transmitted signal. This transmitted signal, this is the receiver. This car has a receiver. So you can see that things, the transmitted signal has been receiving through the three strongest paths. So each of these paths, you can check this blue one, you can see that it has some delay. So since it is very close to the transmitter, it has approximately 0 delay. So you can see here in the delay Doppler grid, you take the grid in the delay Doppler. So you have 0 to 4 delay integers. Doppler side, since Doppler shift can be negative, therefore Doppler integers you will get negative also. So minus 2 to 2 they have taken. So here you can see that for one path, it is a 0. That means delay is 0 approximately. That's why it is being 0th delay grid point, and since it is moving with some speed, so based on that you got the Doppler shift integer as this one. So you can tell that 0, 1 you have 1. If you take the delay as the first, so you can tell the 0, 1 delay Doppler point, I have one channel tab. Similarly here the yellow one, you can see that yellow one is little bit more speed it is moving this vehicle. So that's why what will happen, that if you have little bit more, another this purple one, you can check that this has been reflected by a vehicle which is moving in opposite direction. So as you know that function that you if you represent the Doppler shift, that is there's a function of cos theta, the angle of that arrival. So that you can check the negative sign. So that's why it is negative Doppler shift. And this this radius, you can see radius is slowly decreasing because of the distance is more. Sorry. Because of the distance is more, so the magnitude of the tab is the strength, signal strength is reducing. So this is, you can check that this is delay Doppler domain. So same experiment we have done, same experiment has, so this one is negative. Sorry, the first diagram here you can see. This one is the negative -2 point, this purple one. The second experiment has been done after some millisecond. Here you can check that this yellow part and both these tabs are remaining as it is, and that little bit modification happened through this red one, because red one has been reflected by the backside. What is that? Another vehicle is there, so that's why it has little bit less Doppler shift, because it is moving as less velocity than the earlier one. So what you can check here you can check that after a few milliseconds, even if we can see in delayed Doppler domain, two tabs are remaining as it is, same location, same delayed Doppler location, and approximately same signal strength. However, there is small variation of this another delayed Doppler location. So you can check if you can see approximately the delayed Doppler channel is remaining same with a variation of the time. So that time is known as similar to our coherence time, that is known as geometric coherence time. So it's based on the geometry of our environment, the delay of the channel, you can tell that it is approximately slowly varying in comparison to the time frequency domain. That is the big advantages of delayed of the scenario. So in order to exploit these advantages, so how OTFS can work? OTFS, the transmitted symbol has to be not only it will not transmit through time frequency domain, we have to transmit the symbols. That means we have to symbols has to be multiplexed, that you can tell the transmitted symbols has to be multiplexed in delayed Doppler domain rather than the time frequency domain. So whenever you transmit the symbols in delayed Doppler domain, so you have to convert when you one dimensional, in order to convert the time domain one dimensional in OFDM, we are doing the conversion of time frequency to time domain through IFFT operation. Here what you have to do is we have to convert delayed Doppler signal to the time domain. There are direct transformation method is there, that is known as through Jack transformation. You can tell that delayed Doppler to time, if you have to follow inverse Jack transformation, and time to again delayed Doppler at the receiver side, you have to follow Jack transformation. So that is a direct approach. But this approach will not be compatible with the OFDM modem what we are using now. So that's why, but this is a separate, this is a good approach. I can tell you that it has a lot of other advantages in considering the point of view, implementation point of view, hardware complexity, that we have also verified. And the second one, that is another method that is known as two-step approach. That means you can tell the time frequency. So the delayed Doppler signal has to be converted to time frequency first step. Then time frequency will be converted to time domain in the second step. If you do this approach, it can be compatible with the OFDM model. So how? So I will discuss the second approach. Here you can see that if you transmit symbols will be in the delayed Doppler domain, first you have to convert into time frequency. That will be converted through inverse symplectic finite Fourier transform. So that you can tell that here to here direct. The delayed Doppler to time, as I told you previously, you can remove these two blocks by simply Jack transformation or inverse Jack transformation. But this Jack transformation is replaced by the two-step approach. One is ISFFT, that will be from time delayed Doppler to time frequency. Then time frequency to time, that will be Heisenberg transformation. Heisenberg is nothing but similar to us your IFFT transformation. So this similarly at the receiver, what will happen after transmitting through channel, the received signal will be converted back into time frequency, the time domain signal, through Wigner transformation, and time frequency to delayed Doppler to the inverse of this ISFFT, that is the SFFT. SFFT is the transformation technique that will be converting the time frequency to delayed Doppler. Okay, so here you can observe that this small box is nothing but the part of OFDM. This is a complete OFDM system. So that means we can see OTFS, if you are using considering the existing 5G standard, we are not significantly modifying the OFDM. We can implement OTFS by doing some pre-processing technique that is known as ISFFT, and a post-processing technique that is known as SFFT. So, but there is a lot of challenges also that we can see if when in the implementation will go, when we will do implementation, then we can see a lot of challenges will come into the picture. So here I have mentioned all the transformation that is in transmitter side and the receiver side. So here what is the first point? when you are converting the frequency, this is the frequency and time, this is the delay in Doppler. So that is two types of grids we have. One is time frequency grid, you can check, the delay Doppler grid, the two-dimensional things. So whenever you have time frequency, you can see the time frequency plane. Each of the point is n t correspond to the time duration. Delta f is the subcarrier. So you can tell that m delta f, if there are capital M number of subcarriers, m delta f is the total time duration of the wave. You can take the frame in time frequency. So m delta f is the total bandwidth. And if I have n number of time means symbols, so you can tell the n into capital T, that's the total time. So you can tell that the frame we have considered, that is in the bandwidth is m delta f, time it is capital N into T. Same thing you can see in the delayed Doppler domain. So here you have to quantize it. 1 by nt is the quantization steps of the Doppler. 1 by m delta f is the quantization steps in the delay. Then you have a delayed Doppler grid. K and L that represents the locations, delayed Doppler locations. If you can take this like this grid, you can see that there is being sampled version n in the Doppler domain, m I take in the delay domain. Okay, so then you have the delayed Doppler grid, and this is the then that can be converted by using SFFT, the two-dimensional transformation, SFFT or ISFFT. So in the transmitter side, as I told you, first thing is ISFFT has to be done. Delayed Doppler has to be converted to time frequency. This is the mathematical operation that we will do in the ISFFT. After that, you have to use Heisenberg transformation through using a pulse. This is a transmit pulse that you can choose any pulse like Gaussian pulse, rectangular pulse like that. So this transmitted pulse will be through the transmitted pulse. You can convert this time frequency domain to the time domain, that is known as the Heisenberg transformation. So similarly, that you have already shown here. Here I told you this thing. I have written the mathematical form. These complete things. So then same as the receiver side. Yeah, this is the receive signal. If you transmit what you are transmitting, we are transmitting S of t. S of t, the transmitted signal time domain. If what is the relationship between RT and ST? If you know the channel is in time. Suppose the channel is LTI system. Okay, channel is LTI system. So what the RT and ST relationship? That's the linear convolution. So same here. So similarly, if it is the channel in delayed Doppler, if you do the derivation properly, so you can get that the delay, the channel, this transmitted signal will be related through channel. It has been related with the means you will get the received signal using this equation. This is the received signal. After that, the steps you have to follow. One is Wigner, that will convert this time domain to the time frequency. Then we have to go for the ISFFT to convert the time frequency to delayed Doppler. So time frequency, when you are converting, it is nothing but you can take this as something like masked filter. So you are using a received pulse GRTX that will generate a time frequency in the continuous domain. You can also tell this as cross ambiguity function. And after that, you have to sample it at particular time instant nt and m delta. So you will get the time. You will get now the discrete time frequency domain samples. So if you if you write mathematically, I will tell you what is this equation, the relationship between. Let me show you this diagram. Yeah, what I wrote this is the received signal in time frequency. This is the transmitted signal in the time frequency. The input output relationship between the received signal and transmitted signal through the channel in the time frequency, you will get like that. This is the equation. So here you can see that this, if you do the mathematical complete things, is the relationship between the time frequency, transmitted signal, the time frequency, and this is the time frequency. I have not written the delayed Doppler domain. So now you'll go one by one analysis from here. So here you can see that the time frequency representation of the channel can be, this is the mathematical relationship between the time frequency with this delayed Doppler that you will get through that operation, the Wigner operation, all this. So after that, we have to do the SFFT, Wigner transform. After that, SFFT. What SFFT will do? The time frequency domain, it will convert to the delayed Doppler domain. So we'll go now the detail insight of that. So first point is using ideal pulse. What is that ideal pulse? If I will consider, if you just you will get one term here. Yeah, here. This is the cross ambiguity function between the transmit and receive pulse. So it has some kind of this. It has some. That means you can tell that if you consider a pulse such that ideal pulse means what? If you consider a pulse which will be localized at the time frequency, that is known as ideal pulse. That is something like that. But in practice, it may not be localized in a time frequency. So that assumption of the ideal pulse, you have to choose the GTX, the transmit pulse and receive pulse such that it will be localized over time and frequency. Then what will happen that if it is localized in time and frequency, this equation I will get from here, this equation. That means here, if you I will choose that the ideal pulse means ideal pulse. So what you will get that if I apply over here, it will be reduced into this kind of technique. But if you look into this, what is this meaning? Received signal at nth time and mth frequency is nothing but equal to the frequency response, that channel frequency response at nth time and mth frequency is multiplied with the transmitted signal at nth time and mth frequency affected by the noise. That means here no inter-symbol interference present over here. So it is just simply you can apply one tab equalizer to detect the transmitted signal. So that's why its name is OTFS. You can see now it is orthogonal in time and frequency. That name corresponds here. That means if you choose a localized time frequency pulse, so what you will get, you can, even if you have a highly time varying channel, still we can represent in the transmitted signal in, that means in a this type of form without ICI. You don't have intercarrier interference. Where, however, if you look into the WaveDM, here if you see that, so here there will be always one ICI term will come. That is not coming here in the OTFS, even if you go for the highly time varying. That's name corresponds to from here as OTFS. So I told you that ISI term is not there in time frequency domain, or you can tell this as ICI in considering the WaveDM point. So here, okay, now it is in time frequency domain. After that, I will do what the ISFFT. So, sorry, SFFT operation. If you do the SFFT operation, time frequency will be converted into delayed Doppler. If you apply this operation, so what you can see here is, see the relationship in the delayed Doppler. This is the relationship. This one is the relationship time frequency, received time frequency with the transmitted time frequency. This is the relationship with the received signal in the delayed Doppler with the transmitted signal in the delayed Doppler. So that you can check here from this figure. The receive YKL with the XKL. I wrote the two type of relationship. One is YNM with XNM and another one is YKL with XKL. So you can see now Y. So you have seen here that the relationship in time frequency will be something like this. So here you can observe that. Okay, first you can check here. Here what you have seen is the relationship between transmitted delayed Doppler and the channel tabs at each path. So here you can look into this summation. That is nothing but a two-dimensional circular convolution. So this is, so what comparison you can find in these two type of representation. If you want to do the channel estimation, here you have to do the channel. You have to find the channel at all time and frequency. But here, since in practice we have a few number of cluster in the environment, so a few number tab, few number of paths, so we'll estimate a very few number of channels to get the transmitted signal. So that type of two relationship will give you directly mathematical. From the mathematics, you can see here that yeah, it is correct that we have to go for the more channel for time frequency in comparison to delayed Doppler. So these are the two relationships. And let us come to the next. Next one is I want to represent this equation 4. So we got that advantage of delayed Doppler, right? So let us see how what is the relationship in the vector domain. So if I write this receive signal, I will take a vector. So obviously, that is a matrix vector product. That is in linear algebra. You have to represent the linear equation. So you can see that this Y can be represented receive signal completely. You can take as a vector. Y vector is some matrix channel X plus the noise vector. So you can see here that this channel structure is not so straightforward as that of the other multi-carrier techniques like WaveDM. So this structure, if you follow this equation, what you will see that the channel structure will follow the jth row will have some kind of this. So if you see the complete things, the channel will look like something like this. This is a block circulant structure. Since there are few channel tabs present, it is known as sparse. But in this is an important point. It is a block circulant structure. The channel matrix will follow a block circulant structure. If you will consider an ideal pulse shaping, that means if you write the transmitted vector, this is the transmitted vector, received vector, all are in delayed Doppler domain. Channel is also in the delayed Doppler domain. You have considered channel tabs. Then this channel will be nothing but represented as sparse block circulant structure. If you take one particular example, I took that. Suppose you consider there are 3 number of Doppler points, Doppler winds, and 4 number of delay winds. Let us consider this is the channel impulse response. What you can observe from here, first one you can tell that there is tau minus 0, nothing is the new minus 0. That means this you can tell that H0 is the channel tab which present at the location of 0th Doppler and 0th delay. That means you can tell K0 is the integer corresponding to the Doppler nu naught, and L0 is the integer corresponding to the delay delay shift. Okay, so here you can tell the first path is associated with a delay 0 and delay 0 and Doppler 0. That you can tell the delay Doppler grid 0, 0 location you have H0. And here you can look in the second point that delay Doppler channel impulse. You can see that starting equation. So here you can see, observe here, tau I have written the tau I means, or you can tell that tau 1. Here this 1 corresponds to the delay integer. So you can tell that at 1, 1, here also it is 1 Doppler point. So you can tell that another delay Doppler location will be 1, 1. At that point, you have a channel tab. So channel tab that is known as H1. So if you use this and if you apply this formula over the how you can find the jth row, all the rows. So what you will get here, you will find that small block matrices. So what is the size of this? If n is 3, you will get each of the block matrix of the size n cross n, 3 cross 3. And how many such block matrices will come in each row? M cross m number of block matrix. That is the 4 number of. So just you look in this column, A0, A1, A2, A3. These are 4 number of block matrices that can be generated. Okay, that can be generated using. That means if you write this channel, if you generate this row vector, automatically you will get that this is nothing but the style you will get that this will be nothing but few number of block matrices are coming. Another point you can see that here all these block matrices will be circulant in nature. You can see now this is circulant structure. This A3 is coming here, A0 will be here, A1 will be here, A2 will be here. Again A2 is coming here, A3 is here. So this is circulant structure. So that's it is a block circulant in nature. And since there is few tabs, so it is a sparse block circulant nature. So this is an example of a channel matrix if you are using ideal pulse shaping. So let us come to the point if you are using practical pulse shaping. So if you use practical pulse, in particular, I have used here rectangular pulse. If you write this equation, mathematical equation, rectangular pulse, what will happen? First thing, as I told you here, that if you use ideal pulse, this equation, if you can see, yeah, this equation will be converted into this equation. Okay, there is no interferences. But if you see the practical pulse, this same equation, but you can observe this equation time frequency domain will be converted, can be written as like this. Same equation I wrote, just splitting the two terms. One will be intercarrier interference, one will be intersymbol interference. That means if you use a practical pulse, it will not be localized in the time frequency domain. It will spread little bit more. So how much based on the spreading factor of that pulse, your intercarrier interference and intersymbol interference will come. Intersymbol in terms of the delay, how many symbols are interfered in the delay axis, how many symbols are interfered in the Doppler axis. Based on that, you have ICI and ISI. And another point, this is the representation in the time frequency domain. Same representation we can write in the delayed Doppler domain, equation 6. Now you can see here, you just compare, this is the expression in the delayed Doppler domain. That means this is the relationship, the transmitted symbols in delayed Doppler Okay, the relationship between the transmitted symbols and delayed Doppler domain and received symbol in the delayed Doppler domain. This, just look into this relationship, and I will tell you what is beta I k comma L. This is a phase shift that you can take phase factor, which depends on kth Doppler and Lth delay. So here you just look this equation 7 with that ideal pulse here, this one. Here you, as I told you, that this is a two-dimensional convolution, circular convolution. However, here you can check here, this is not a two-dimensional circular convolution because of this beta I k comma L. Since it is depending on k and L, this thing will not hold. So that's why what will happen, you can tell that you cannot represent the channel matrix in a block circular structure as like your ideal pulse shaping. But here the difference you can see, if you considering pulse shaping technique in time frequency and delay Doppler, here you can tell if you estimate this channel. Okay, if you estimate the channel and this phase, you can easily decode the data, which is very difficult in the time frequency domain because of the presence of ICI and ISI. That you can see, that you can think in another way, that the ICI and ISI in the time frequency domain, which is happening, that will be reflected in the one phase factor. That's it. If you know this phase factor beta I, so you can do all these things. So, but in presence of ICI and ISI, if you do this kind of detection in the time frequency domain, you will get significant problem. However, if you do the detection in the delayed Doppler domain, it will be very easy and you will not get any issues. No interference is there here. So that is a very good thing, the very good advantage point in the, you can tell, in the delayed Doppler domain. So let us write this equation in the vector matrix multiplication. Same thing we can write. So in particular, I took one good OTFS, that is known as CP OTFS, similar to that OFDM, CP OFDM. You can take the CP OTFS. Here after Heisenberg, you add CP based on the same as your how many delay tabs are there. And here you remove the CP. So you will get received signal in time domain, transmitted vector in time domain. And this you write all the transmitted symbols you can represent in matrix form. Okay, so that I'm showing here. So transmitted symbols in delayed Doppler, if you represent as a matrix form as M cross N matrix, M representing the delay dimension, N representing the Doppler dimension. If you do the ISFFT operation, nothing but you can see, if you will express that summation equation in the matrix form, you can see that delayed Doppler matrix will undergo both IFFT operation and FFT operation. That means the rows will be go IFFT and the columns will go in the FFT. Then you will find the time frequency domain. This is the symbols in the time frequency domain. After that, so you can have to do the this is next point is the Heisenberg transformation. Heisenberg is nothing but you can see that this is nothing but just the IFFT operation. Just you can, if you apply that Heisenberg operation, you have to use also the diagonal. Sorry, the means the pulse matrix. So pulse matrix is nothing but diagonal matrix, is a sampled version. All these points are sampled instances. You have considered the transmit pulse. So the diagonal matrix. In particular, if you consider rectangular, this will be identity. So this will identity means this will be gone. So that means you can simply tell that FM Hermitian is nothing but what? IFFT operation on the time frequency domain. That's it. If you are going through some diagonal matrix, some other than some rectangular pulse, then here some matrix will come. That is a diagonal matrix where all the diagonal elements are not equal to 1. Some other values you may get. Okay. So now after that, the transmitter side. So once you got Heisenberg transformation in the time domain, you can represent in the vector domain, the transmitter side. Then, as I told you here, once you have a vector domain in the transmitter side, this is the time domain signal represented in the vector. Then you, after doing all this addition CP, removal CP, you will receive the signal in the time domain. So R is a vector in the time domain. That will be written as this equation. This is the received signal relationship, the transmitted vector in the time domain. This H is the channel in the delayed Doppler domain. Now there is a catch. This H is how you will get this H. This H is can be written like this. This H is the summation of P number of terms, where P the number of paths. Each term has one channel tab, and the delay in Doppler. So delay is affecting the cyclic shift. This is a forward cyclic shift matrix that is being characterized by the delay. If according to the delay shift, this will be shifted. This cyclic shift matrix. You can tell this is also a circulant matrix. This will be cyclic shift. You can see here, this one is coming here like this. So again, another shift. This one will be shifted here. This one will be coming here. This again, this 0 will become here like this. It will happen. There is some cyclic shift. You can see that forward cyclic shift. So this matrix will be pi. And another one is delta. Delta is a diagonal matrix where each element of the diagonal is been nothing but this one. Z, this is the factor, Twiddle factor you can tell, e to the power z 2 pi by mn. So this factor, that means Li and Ki both in addition to the channel tab, the complete thing is a channel matrix, which is a mn cross mn. So here you can see that this is the channel matrix in the delayed upload domain. So after that receive signal, after that we have to do the Wigner and SFFT. If you do the Wigner and SFFT, what will happen? These things will happen. Wigner means this is again known as FFT operation. Okay, and here through Wigner means you are doing means you have to consider the receive pulses. This is again the diagonal matrix of the receive pulses. Okay, so after that, what will happen? After that Wigner transformation, you have to do the SFFT operation. SFFT is the reverse of the ISFFT, right? So in the ISFFT case, you are doing IFFT finding in rows and FFT you are finding column. Here you do the reverse. FFT you find row wise and IFFT you find in the column wise. That is just reverse. Here this side Hermitian, this side is not. This side is FFT. Here this side is IFFT, this side is FFT. Okay, then you apply all these things. Finally, if you write this vector form, you will get this equation. This is the receive signal. So previously I have shown you this the receive signal in time domain, transmitted signal in the time domain. Now what I have shown you, I'm showing you that this is the receive signal in delayed upload domain, transmitted signal vector in the delayed upload domain. Here the channel will be nothing but the effective channel matrix in the delayed upload domain. This is the channel matrix, effective channel matrix in the delayed upload domain that you can find by applying the IFFT operation here. Here this SFFT operation and converting into the vector form, you have such kind of this Kronecker product will come. So that will give rise to this matrix. So you can clearly observe here. So if you see, this is the equation in the practical pulse shaping. However, this is the equation in the ideal pulse shaping. Okay, now you can look, yeah, this. So here I told you that ideal pulse shaping, this H is following a block circulant structure. However, you can check now. Here, this H is not following a block circulant structure. These are some different structure. Okay, so that is the difference between if you are considering ideal pulse in comparison to the practical pulse shaping. But in practice, you have to go for the practical pulse shaping. But in through all the research analysis, you can do this both by a lot of to develop a lot of other algorithms. So let us come to this I have demonstrated completely the framework of OTFS system. That means the relationship between the transmitted symbol and received symbol for ideal pulse shaping and practical pulse shaping. So now we'll go using this model. If we go towards various research directions. So one is on the research, all these things. I'm not going to detail of that. You can find the details in this paper. So what we have developed whenever you are going to do the channel estimation, you have to do either by pilot embedded, pilot based channel estimation or blind or semi-blind. Blind, semi-blind are very difficult for OTFS. The reason is channel is highly time varying. So you have to go pilot added. In pilot, if you transmit in the same structure pilots and data, so there will be spectrally inefficient because you are trying so that means few slots you are dedicating for the pilot. But here what we have done is each slot we have pilot and we have the data, that is known as superimposed pilot. Here you some kind of this is the frame structure of the delayed upload domain. So if you do that, you will face lot of challenges like data and that is the data and pilots. So that will be interfering. So that will lead to interference during channel estimation, interference during data detection. So that has to be mitigated by applying some technique. So we have done some technique over here, applied in this paper, so which are going to be very effective. So any interested candidate, you can follow this one. So next work what we have done recently, that is we have also focused on the sparse signal recovery. As I told you that channel is sparse in nature. If you can convert the channel estimation to a sparse signal recovery problem, we can get better advantages in addition to the existing channel estimation technique. But whenever we are doing that, we have to see one point, that we have to not only estimate the channel, we have to estimate the channel locations. That means if you can express the channel complete information through a vector, so here it's meaning that we have to estimate all the non-zero locations of this vector. That's the job of the channel sparse channel estimation technique. Here we have proposed a low complexity sparse channel estimation technique, where the delayed of the locations are not known prior to us. We don't know how many delayed of the locations are there previously to us, and we don't have any knowledge about the delayed of the locations. So you can see this paper, wireless later you will get the detailed technique how we have estimated the channel. Next direction of the research in the towards equalizer. So in particular, linear equalizer is, that very efficient in terms of implementation point of view, that is zero forcing, MMSC. Okay, so we have also developed the equalization technique, that is low complexity. Why low complexity? Because if you go for the equalization technique, in particular zero forcing and MMSC, it includes one inverse of this kind of matrix. Inverse of this matrix is too much complex because its size is too high, very much high size. So you have to develop some low complexity algorithm. So now the question is how we can develop. So here we have considered ideal pulse shaping technique. Since we know that the ideal pulse shaping technique follows it is following a block circulant structure. By exploiting the block circulant structure, we can find the low complexity data detection technique. We can develop a means we can efficiently calculate the inverse of these matrices. So you can follow these papers. So this is also the second paper, is also one of the best reading article in IEEE Communication Society. Next one is the theoretical bit error. That is also we have derived in theoretical bit error rate. What we have derived in OTFS for zero forcing equalizer. So we have done the derivation in bit error rate. Bit error rate, you know that as a wireless communication engineer, we require this expression to develop a lot of intuition, to create a lot of intuition about various detection techniques. So here you can check that this work we have done. So next, another work on OTFS is we have mixed the two technologies, like that RIS or IRS, that is reconfigurable intelligent surface or intelligent reflecting surface. It can be that is I think some talk was already there previously on IRS. So you can club OTFS with IRS. Okay, that is not similar as your WaveDM technique. Okay, that is lot of challenges, extra challenges you will get in WaveDM technique. Just a minute. Hello. I mean, talk.
Yes.
Okay. So here, so you can see that you can see here that if you go for ZF and MMS equal, we have developed some low complexity equalization techniques. Low complexity equalization technique, okay, for IRS and OTFS based systems. So here you can see this paper. So this is actually currently in major revision, so it has not been published till now. We have developed a low complexity in comparison to the existing techniques. So next work is little bit on hardware architecture of OTFS. So hardware architectures on OTFS, what we have done is we have developed a low complexity hardware architecture of OTFS transmitter. So here in this work what we have done is we have focused on the how we can consider, since ISFFT, as I told you, transmitter side we are using ISFFT. ISFFT is nothing but the use of FFT and IFFTs. So the low complexity techniques, low complexity FFT and IFFT algorithms we have developed and implemented on the FPGA that you can see in this paper. So and another work that you can check here, that recently this work has been accepted in IEEE SPCOM. So here we have developed what VLSI architecture for OTFS systems, considering two different architecture. As I told starting, we have a direct approach, we have an indirect approach. So if you go for that two approaches, two different architectures you can get. So the comparison what we have done is, if you compare this on FPGA, what we got that it is more efficient. The first direct approach is more efficient in comparison to the two-step approach. That's why I told that direct approach is very good in terms of hardware implementation, but lot of changes we have to do in the modems. So you can go for the, now we can tell you some research directions. Here you can go for OTFS IRS. So IRS OTFS is not a straightforward direction. Lot of challenges are existing here in terms of channel estimation, detection, and all. And another direction you can see that using OTFS 2.0, whatever I told that direct approach, that is nothing but OTFS 2.0 in addition to the ISFFT two-step approach. Okay, so you can go for that research direction. That is also blooming now, that is getting a lot of research attention on the wireless systems. Another, I can tell you some key references. You want to, someone want to start the OTFS. So first you can follow this paper. Yeah, this Professor Mohammed, SK Mohammed, IIT Delhi, is a very good paper on how you can get the derivation of OTFS from the first principle. And second, you can go for this paper. This one, embedded pilot channel estimation, and you can follow our paper. This one you can follow to complete the how you will get the complete transmitter receiver equation in practical pulse shaping. Okay, that is in this paper. So similarly, you can follow this paper. In addition, this paper you can see how you develop the equalization techniques, all these things. So these are some key papers if you want to start research in OTFS. So first point I can suggest you go for these 6 papers. It's very easy to follow. So you can easily find this is a simple paper, you can see less difficulties. You can easily find many insights of the OTFS system. Okay, so if any questions, so I am we can discuss here.
Is it over, Dr. Himanshu?
Yeah, it is over. If you have any questions.
Okay, thank you. So maybe floor is open for any questions. So I think 100 plus faculty members are here. So any question? I think in between your topic may be a little bit new and complex. So in one round of session may be difficult. So recording would help go through it.
Yeah.
So any question from any of the faculty member? You can raise your hand or directly open the mic. In the meantime, I have one query to you. Like as we said that this kind of waveform may be considered for 6G. So is there any effort from our side that we push this in 3GPP? Is there any way we are able to do that?
Yeah, we can do. Actually, we have to think a lot of that. If it is possible through like this structure, existing WebDM, if you can develop something using existing WebDM modem, so we don't want to change anything in the modem. If you can do something that use that same existing modem with some additional blocks here, like here 2 blocks are there. If you can do that, and another challenge you can get, like in WebDM, there's some advantage of one tap equalizer. That is, you can tell that if you receive signal at some frequency slot, you can detect that easily. So that type of facility is not there in OTFS. That is one challenge. If you can get that, so I think we can push these things to the 3GPP.
Okay, I think
Some challenges.
so is IIT Dhanbad a member of 3GPP somehow, or
3GPP, yeah, we'll going to the member of 3GPP next time. I mean TSDSA, I think you are telling, right?
okay?
Or
So TSDSI is of course is one of the consortium member of
of
3GPP. So are you interacting with 3GPP as a
uh, no, actually, we have not that much of interaction with 3GPP, but recent meeting I have seen, the documents
okay?
are regularly watching. Recent meeting, what I have seen, they have focused on ISAC. But what I have seen that till now, OTFS means they are planning, they are pushing OTFS to be come into next generation. That is hard, but it may come after maybe some release. It may come. The thing what I heard is it may come with existing WebDM modem. So they are not going to change complete modem. So
Okay,
existing WebDM modem will be there. With that OTFS will come, because if you say change the complete modem, lot of means hardware has to be replaced, and that may be a cost. It's not be cost effective. So that's what I heard the complete. But we are going to take this membership shortly.
okay, okay. So maybe you can be part of.
Yeah, yeah, I am.
I mean, at least the TSDSI, so that in their meetings, perhaps,
Hmm.
I mean, something can be done. Some heads up would be possible.
Some, yeah.
Yeah.
Correct. Right.
Dr. A. Jawahar Saab has opened the video. Do you want to say, sir, anything?
No, sir. No, sir.
Okay, thank you. Thank you. Any question? Any more question? Okay, there is a raised hand by Srinivas Rao Saab. So please,
Hello, sir.
yeah, go ahead, sir.
Hello.
Sir, am I audible?
Yes, you are audible.
Sir, you told by adding some blocks in the OTFS with the OFDM compatibility.
Yeah.
So I have seen multiple papers are there, including channel estimation techniques, equalization techniques, and different performance analysis of this OTFS.
Mhm.
So what kind of blocks can be included here, such that that can be leading to the 3GPP standardization specifications?
Yeah, this one, this ISFFT and SFFT block.
Okay, so I think many like models are there for ISFFT and SFFT blocks. So where we can improve by replacing this ISFFT, and by what kind of methods? Because
No,
when
that
we
means
use
that we have to think actually. First thing is how to frame the frame. That means, see, if we are going to replace whatever existing modem, if we are going to use that, one negative point we will see that lot of resources will be wasted. What is that? The CP. If you are
okay,
making the time frequency domain, you have the OFDM blocks, right. You have
yes,
if you see the OFDM frame, you have the time, each time you have all the subcarriers. Another time you take that OFDM blocks, like the OFDM blocks are there, so it will make a frame. So that you take as an OTFS frame. Then if you go for that structure, each time slot, each subcarrier blocks, you will see some CPs will be added. So every OFDM you will see the CPs are there. So that is a negative point of if you go directly just replace this OFDM with this. So then you have to be very much careful about the CP. So if you go separate OTFS modem, then you have a CP duration which is length is similar as that OFDM modem. As I show you here some this thing. So that is a negative point of directly replacing the OFDM. So that's where a lot of things are going on. If you replace this directly OFDM, then you have to be on the resources. You have to lose many things. Okay, so that's what one paper is also there that is suggesting this thing.
okay.
Okay, there is another raised hand by Dr. Laishram. Sir, please go ahead.
Question. Which software is used for simulation for performance analysis over using this OTFF FS system with simulation? is
Which
used.
simulation?
Yeah, sir.
You can do simulation. You are telling in a platform like language, MATLAB or C, Python.
Yeah, for this analysis, OTFS.
Okay. You can do anything. You can write this, implement. You can implement this. We have done in MATLAB. You can do in Python also. You can do in C also. Not a problem. Same as what you are using platform for WebDM also. Same you can use. All the algorithms you can develop. Any platform you can use.
Okay, sir. Thank you.
Okay, so any more query or question or anything? If there's no more questions, then I thank Professor Himanshu, and I also request Sanjay to offer formal vote of thanks to Dr. Himanshu. Madhukar?
Yes, sir. Yes, sir. Dr. Himanshu Mishra, Sri Kumar sir, and esteemed participants. On behalf of the FDP participants, we extend our heartfelt gratitude to Dr. Himanshu Bhusan for his exceptional contribution in presenting this contemporary and advanced topic. The chosen subject is highly relevant in the realm of wireless communication and represents a significant way forward. Your presentation showcased a profound understanding of the topic, providing deep insights. Such diverse and knowledgeful talk will certainly enrich the overall content of this faculty development program on. We extend our sincere thanks to all the participants for their valuable time and participation, which undoubtedly contributes to the success and effectiveness of this faculty development program on 5G. Together, your diverse knowledge and engagement elevate the overall content and experience. Once again, thank you to Dr. Himanshu Bhusan Mishra and all the participants. Your dedication and contributions are truly appreciated. Warm regards to all. Thank you, sir. Thank you all.
Thank you.
Okay.